Before we go any further, there are a few things I'm going to assume are true. All right, these four things here. Now, the last three, those are all standard algebra properties. And the first one just says that the sum of two integers is an integer and the product of two integers is an integer. Right, now, these are all things that are usually just presented as facts in algebra classes, but some of them are things that actually should really be proven first. Doing that is something you would normally see in like a more advanced class in either abstract algebra or real analysis. So we're just going to follow the algebra custom and accept them as true. All right, so we're going to start off with a pretty straightforward statement here, right? The sum of two odd numbers is an even number. Now, this is pretty clear to me, but when you're just starting off, right, it can be helpful to rewrite something like this into a purely if-then form. All right, so for our theorem, that would be if two numbers are odd, then their sum is even. Okay, now to prove this, I'm going to use something that's called a direct proof. Right? This method relies primarily on forms like universal instantiation and modus ponens to form a straightforward logical chain of arguments that will take us from the premises to the conclusion. Right, now, I'm going to talk a little about some general properties of a direct proof in a minute, but I want to actually walk through this proof first so we have it as an example to refer to. All right, the theorem says that we're talking about two odd numbers. So I'm going to start by using universal instantiation to get two arbitrary odd numbers to work with, right? So I'm going to say proof that A and B be odd numbers. Now, that's a good start, but it doesn't really give me much to work with. So I'm going to follow this by using what the definition tells me about these numbers. So by definition, there exists integers m and n such that A equals 2m plus 1 and B equals 2n plus 1. Okay, next, think about what we want to show. Right, the theorem makes a conclusion about the sum of the two numbers. So a logical next step is to look at their sum. So I would say then A plus B equals 2m plus 1 plus 2n plus 1, which equals 2m plus 2n plus 2. Okay, now we're getting somewhere. Remember that we're trying to show that this sum is even, and I'm seeing a lot of 2's in that expression. If we factor them out, we get A plus B equals 2 times m plus n plus 1. All right, now I can go to the definition of an even number, right? Since m plus n plus 1 is an integer, what we've shown is, let's write it, we've shown that A plus B, the sum of the two numbers, can be written as 2 times an integer. So by definition, So my spelling's getting, my handwriting's getting a little sketchy here. Definition, the sum is even. And that the sum is even, that's what we wanted to show, right? So the proof is over. I've really kind of ended it with, therefore, by definition, the sum is even. That's good. Or you could go ahead and put something specific here at the end, like QED, right, which we talked about in the last lecture, as a way of showing that you've finished the proof. Okay, so I've written out the complete proof here, right? Hopefully you've already read this out yourself in your notes, just so that we have a clean version so I can pick out some specific points. Right? When you're doing a direct proof, a common first step is to use universal instantiation to assign variables to specific instances of the thing that the proof is giving us information about. That's what I'm doing here in this first sentence. You notice to do that, I use a new word, right? This word right here, arbitrary. In math speak, arbitrary is a word that we use to mean there's nothing special about these two numbers that I've picked, other than that, in this case, they're odd numbers. Right? This is one of those common phrases that we discussed in the last lecture that you'll see used over and over again. So my next step was to think about what it means for two numbers to be odd. And again, I used universal instantiation combined with the definition to get these two integers, m and n, that the definition says have to exist. Right? Now, an important thing you should notice here is that when picking these variables, I'm doing two things. First, I'm clearly stating what each one is and where it came from, right? They're integers, and I'm pulling these from the definition. And second, I'm being careful never to reuse a variable. Once you've assigned a meaning to a variable, you can't turn around and reuse it for something else. So for example, it would have been incorrect to try to say a is equal to 2m plus 1 and b is also equal to 2m plus 1. A and b are different numbers, so I needed different variables here to represent them. Now, at this point, I've largely completed the setup of the proof. So my next step is to go to the other end and look at what I'm trying to show. Right, that the sum of the two numbers is even. So this is telling me where I need to end up. Right, in this case, the only thing we have to work with is the definition. Right, so I know that in the end, I need to show that the sum is equal to 2 times some integer. Right, and finally, to bridge the gap between the premises and the conclusion, I looked at the sum of the two numbers, a and b, and then I use some algebra to show that the sum has that property that the definition said I needed for that sum to qualify as even. Okay, so here I've got a general outline of what we did, and I've said this before, and I'm going to want to repeat it here. Proofs are like the word problems of higher math. There is no one universal way to write a proof. However, when you're doing a direct proof, certainly a lot of the ones we're going to be looking at in this chapter, this is kind of a good general approach, right? First, I think about where I want to end up and what I have to show to get that result. So yeah, a little bit, I'm actually kind of starting at the end, right? Because I want to have firmly in my mind where I need to go with this. Right, then I start the proof by instantiating a specific instance of the thing that we're talking about. That was odd numbers in the proof we just did. And then I apply definitions or already proven theorems to work my way in a series of logical steps to that final conclusion. Okay, so what's next? We're going to continue looking at some examples, right? Just like when you're learning to do word problems, having a bunch of examples to kind of filter problems that you're trying to do on your own through is helpful. So we're going to continue our process here by looking at some additional proofs relating to odd and even numbers.